Anybody objects to having 2 lecture hours on Monday at 1:40? Yeah, okay. So Monday 1:40, somebody has a class, so no. Yeah. Okay, so the next discussion I would like to make, I mean, I had to just think a lot about it, whether to skip it or not. It will be a mathematical derivation. The derivation will be whether, you see, here we calculate the most probable numbers NR. I always claim since the beginning of the lecture that the most probable and the average, they will be the same. But I never proved it. So now we can make a proof. It will be a long computation. From the perspective of statistical physics, I don't think it will give you too much insight. So I was kind of tempted to skip that. But I think it's really nice to show one aspect of statistical physics because you see, if you study electrodynamics, you have the Maxwell's equations and you just apply them. In classical mechanics, either you have the Hamilton's equation or Lagrange equations. You know where to start this. And then it's more or less straightforward. The difficulty in thermodynamics or statistical physics is it's not so straightforward most of the time. You have to just use many things from many different areas. And the next derivation is a nice application of your mathematical physics course. That's why at the end I decided to go over it. Now the question we are trying to calculate is, okay, we wrote this number, which is basically the number of microstates that have the number of distribution of microstates in our ensemble, which corresponds to that number NR, which is n factorial divided by n0 factorial, n1 factorial, etc. And we already, in the last hour, we calculated the most probable set. And now I ask the question, what is the average value of this NR? Well, it's kind of easy to calculate, to write down at least, not calculate. It's just sum over all possible sets of this number NR multiplied by the probability of, no, let me write it in this way. Probability of that set corresponding to my ensemble, which will be sum over all sets NR. Let me put a prime over here. I'm not summing over all possible sets NR. I'm summing over all possible sets of NR consistent with my constraints of NR, omega of NR divided by prime omega of. So this is what I would like to calculate. And once I calculate this, the purpose is to show that this is equal to an R star. That is the eventual aim. So basically proving my claim that in the thermodynamic limit at least, any deviations from the most probable state will be negligible. So let's proceed. You see, there are two things I have to calculate. One, the sum of omega and R over all possible sets NR, and then multiply omega with NR and sum over all of them. So rather than doing that, I will do a trick. Let me define a different one, omega bar. Let me define it this way. I just introduce these numbers. Well, the reason why I introduce those numbers is when I set them to 1, I recover my omega. But now, since they are just arbitrary numbers at the time being, I can take their derivative. Well, if I take their derivative, it will just bring down some n0, n1, or n2. So basically, nr times, well, let me also make one small change. This is ni. And the reason why I make that change is when I show you this symbol nr in curly brackets, it's just a collection of numbers. Ni is just one of them, the one corresponding to the ith state among those nr numbers. So that's why I would rather use the symbol I. Now this ni omega bar, this is basically omega I del over del omega I of omega bar. And when I set all omega r's to 1, this is nothing but my omega. This is why I introduced that omega bar, to be able to use this trick over here. So if I can calculate omega bar, I don't need to calculate two things in the denominator and in the numerator. If I just calculate omega bar, I'm done. So now Ni will be basically sum over Nr of omega I del over del omega I omega bar divided by sum over Nr omega bar. These are all primed, so this will be omega I times del over, of course, when all omega I is equal to 1, logarithm of so I calculate this sum for omega bar, take its logarithm, take the derivative with respect to omega I, then set all the omegas to 0, to 1. That will give me the average of Ni. Since I'm setting all the omegas to 1, I don't even need to multiply by this omega I. So any questions here? So now my task will be to calculate, let me use gamma, sum over nr of omega bar of nr and omega r. This is my next task, which will be n factorial omega 0 to the power n0 divided by n0 factorial omega 1 to the n1 divided by n1 factorial, and for all the rest. Still, well, you see, if there were no constraints on nRs, it will be an easy computation. You see, I can, summing over n0 will just give me e to the power omega 0. Summing over n1 will give me e to the power omega 1. They're just nothing but the Taylor expansions of the exponential. But I have two constraints that I have to impose. n0, n1, n2, etc. They are not independent of each other. Now, but keep in mind that, does anybody know, how can you write this expansion? And it's just a binomial expansion. And this is, if I write it explicitly, this is n factorial divided by k factorial, k1 factorial, k2 factorial, a to the power k1, b to the power k2, but with the condition that k1 plus k2 is equal to n. This is just a binomial expansion. Well, we can generalize this a1 plus a2 plus etc. to the power n will be sum over k1, k2, n factorial divided by k1 factorial, k2 factorial, a1 to the power k1, a2 to the power k2, a3 to the power k3, and all the rest, with the constraint that sum over ki is equal to it. You see, the second best thing I could have, you see, here in my initial summation that I'm summing over these NRs, if I had all the NRs independent of each other, it was easy to evaluate because then I would have just the product of exponentials. But that is not the case. I have two constraints. One of them is that the sum of those NRs should be equal to curly n. That's one constraint I have. If that was the only case, again, it would be easy because in that case, I would have just this multinomial expansion. But I have one more constraint. So that kind of makes my life hard, let's say. But let's do a trick. Let me define something else. Let me consider this one. Yes, I'm summing over these NRs. On one hand, I have this condition that sum over NR should be capital, and on the other hand, I have NR times ER should be equal to capital N times the average energy of my system. Of what I am summing is n factorial omega 0 to the n0 divided by n0 factorial, omega 1 to the n1 divided by n1 factorial, etc. Let me add another sum, but this time over all possible values of u. If I add this sum over all possible values of u, effectively I'm removing this constraint. Because when I'm summing over all these multiples, this sum can have any value because I'm also summing over u. But this sum is not the sum I want. I want this term. So let me multiply all this thing by z to the power nu. You see, when I'm summing over all possible values of u, now I have a different variable z. You see, first I introduce these omegas, omega 0, omega 1, omega 2, which I will eventually set to 1. Now I introduce another variable, z. I multiply each one of these terms by z to the power nu. So that if I can calculate this whole sum, make an expansion over z, and just go and pick up the coefficient of z to the power nu term, I obtain this sum with double constraint. Well, instead of that nu, I can, of course, just substitute sum over nr er. So that term becomes sum over nr with the only constraint, this one. You see there I have a sum over the sets of nr, and then with two constraints, then sum over one of the constraints. So basically, this sum can have any value. So that two sums is actually just a single sum with a single constraint. Inside, I have n factorial omega 0 z to the power e0 to the power n0, omega 1 z to the power e1 to the power n1 divided by n0 factorial, n1 factorial, etc. Now, this is nice because this is nothing but the multinomial expansion. This is equal to omega 0 z to the power e0 plus omega 1 z to the power e1 plus over all possible microstates of the system raised to the power Curlian. Let me just call this f of z to the power Curlian. You see, now I carried out the summations exactly. You see, this function, now the next thing I have to do is I need to expand this fz to the curly and in a Taylor expansion in z and pick up the coefficient of the term I want. This is nothing but the generating function of the sum that I am actually interested in. So any questions up to here? So this is the idea of generating functions. Now we can pick up the coefficient of a particular term using a complex analysis, the Cauchy integral. You see, what I'm interested in is the coefficient of z to the power nu. Let me just add 1 to this term, f of z to the power n. Now, if I calculate the residue of this term at z is equal to 0, that is the coefficient I'm interested in. But the residue, just Cauchy theorem tells me that residue is nothing but this. If I integrate around z is equal to 0, it will give me 2 pi I times the residue. So if I divide by 1 over 2 pi I, this is actually my omega bar. Okay, just one warning. You see, up to here, I'm just treating all the powers of z as if they are integers. Because if they are not integers, then I have the branch cuts, etc., all that problem. But that's not a serious problem, at least from a physics perspective, because I just can choose a unit of energy such that all the E0s, E1s, they are integers. Integer multiples of that given energy. So just treating all the exponents as integer is not really a big issue for me. Now, how to calculate this integral? We have to evaluate this integral somehow. First, let's try to analyze what this integral looks like. I will also set E0 equal to 1. E0. Well, I'm just fixing the ground state to have 0 energy. I'm shifting my energy, which is less than E1, less than E2, etc. So now, at z is equal to 0, you see, if you look at z is equal to 0, and I will assume omega i's to be very close to 1. Eventually, I will set them to 1 anyway. The reason why I'm saying close to 1 is I would like to take the derivative with respect to omega, so I need to know how they behave when omega is very close to 1. That's enough for me. Now, since I set E0 to 0, this is 1. So when I set z is equal to 0, everything here is 0. So I'm just left with 1. F of 0 is 1. Almost 1. When I set omega to 1, it will be 1. Then as I increase z, fz will increase. So fz will be, everything over here is positive. Or along the real axis, or along the positive real axis, everything is positive. Omega 0, omega i's, they are all 1. So here the z to the e1, z to the e2, etc., they are all positive powers of z. So as I increase z from 0 to 1, from 0 to positive values, fz will be increasing. So here I have fz, which is an increasing function of z. And keep in mind that this capital N is huge, so it will be increasing very fast. On the other hand, if you look at this 1 over z to the nu plus 1, it diverges. You see, schematically, along this real axis, fz starts from 1 and increases very fast, whereas 1 over z to the nu plus 1 starts from infinity, and then it goes to 0. This is 1 over z to the nu plus 1. And since n is huge, nu will be huge, this also goes to 0 very fast. Well, if you multiply them, what you will end up having is a function along the real axis like this. It will start from infinity. Well, fz goes to infinity much faster. And eventually it goes to infinity. Here there is a minimum. This is along the z-axis, by the way. Along the z-axis, this function fz will have a minimum. Now this integrand will have a minimum, sorry. Now this is an analytical function. Everything is analytical. So if you treat z as a complex number, you see, okay, so let me put it this way. This is real value of z, this is imaginary value of z. We know that along the real value of z, there is a point where it is a minimum. So here at this point, it is a minimum. Along the z-axis, but complex analysis tells me that analytical functions cannot have local minima or maxima, which basically tells me that since this is a minimum along the z-axis, it has to be a maximum along the vertical axis. So that point is a maximum along this direction. It's a minimum along this direction, but a maximum along that direction. And it will be, the change will be very sharp because capital N is huge. So it will have a very sharp peak along the imaginary z-axis. Now remember what we are trying to evaluate. I'm trying to evaluate this loop integral around the closed loop around the z is equal to 0 line. So I can choose my integration contour to pass through that point. That is the saddle point. So I will integrate my integral along this path. The value of that loop integral around the path enclosing z is equal to 0 point is what I'm looking for. But again, keep in mind that along this path, the maximum value is right at this point. There is a huge peak at this point along this path. So the contribution from other points will be negligible. So that I will only receive, the dominant contribution will be around this point. This is where I have the dominant contribution. Because there the value is huge, in other parts it won't be so large. But if that is the region of dominant contribution, because there is a huge contribution from there, Well, I can change my integration region to this one. Well, you see, if I can be sure that there are no poles anywhere else, I can deform this red contour to that blue line. But I don't know if there are any other poles or not, but I don't even really need to know that because since the dominant contribution over here will be from here, whether I integrate it over the red curve or the blue line, well, both receive the same contribution from this region, so they will both have the same value. So this is what's called the saddle point approximation. You see, very close to that point, what this function looks like is actually a saddle. You see, it's a minimum if you go along this line, but it's the maximum if you go along this vertical line. So that's why it's called the saddle point approximation. We are choosing our contour to go through this saddle and just picking up the region where there is a maximum contribution to my integral. So this is what I'm trying to integrate. I'm approximating this to 1 over 2 pi I. If I set z is equal to x plus iy, I'm integrating from y is equal to minus infinity to y is equal to plus infinity f of x0 plus iy divided by x0 plus iy to the power nu plus 1 diy. And x0 is basically this point over here. Now let me again write my integral as a logarithm. So let me write this as 1 over 2 pi y is equal to minus infinity to plus infinity e to the power g of x0 plus iy dy. This is what I'm trying to evaluate, where this g of x0 plus iy is equal to n logarithm of f of x0 plus iy minus nu plus 1 times logarithm of x0 plus iy. Let me keep the z. And again, keep in mind that f of z is this function over here. Now, first, let us find what is x0. To find x0, I just need to take the derivative of g with respect to z, g prime, evaluate that z is equal to x0 is 0 along the real line. This should be 0. But this is equal to n f prime of x0 divided by f of x0 minus nu plus 1 over x0. This should be equal to 0. This is how we can determine x0. Well, we know what, well, let's keep it this way for the time being. x0 satisfies this equation. Well, we know what f is, so we can just put in f over there and obtain an explicit expression, but f already has a complicated expression, so let's keep it this way. And now let me expand g of z around z is equal to x0. So this will be g of x0 plus g prime of x0 multiplied by z minus x0 plus g double prime of x0 multiplied by z minus x0 squared divided by 2 factorial plus all the other terms. But you see, x0 is chosen such that this derivative is 0. This term is 0. So g of z is approximately g of x0 plus g double prime of x0, z minus x0 squared over 2 factorial plus the remaining terms. Now I can put this all in my omega bar. This is equal to 1 over 2 pi from minus infinity to infinity e to the power g evaluated at x0. Now this is a constant independent of y. Then I have e to the power g double prime of x0. Well, instead of z, when I replace x0 plus iy, x0's cancel, I end up minus y squared over 2. And then I have other terms which I ignore because, as I said, this integral will receive, this will be huge. So it will only receive contributions around y is equal to 0. The other terms have higher powers of y, so their contribution will be even smaller. dy, so omega bar is 1 over 2 pi e to the power g x0. The remaining integral is just square root of 2 pi over g double prime of x0. Remember, omega bar was, okay, g is this one over here. And omega was omega bar evaluated omega is equal to 1. All the omega i's being equal to 1. So basically, and once I obtain omega, the average of n I was nothing but derivative with respect to omega I, logarithm of omega bar, evaluate that all the omegas equal to 1. So basically now I have all the ingredients I need. The only thing is I have to just put them back in and try to simplify as much as possible. So, let's see. Now, I need the logarithm of omega bar. Now, the logarithm of omega bar will be gx0 minus 1 over 2 logarithm of the second derivative of gx0 plus some constants. Now, since I'm interested in the derivatives, I don't really care about those constants. This gx0 is the first term. This logarithm, the second derivative is 1 over the square root. Now, what is g? This is n logarithm of f of x0 minus nu plus 1 logarithm of, well, I need to calculate, sorry. I think I will leave the rest as a homework. It's just a tedious long, just take this from there, that from the other equation. Now, the points I wanted to emphasize we had already covered. So you see, we had used many tricks from your mathematical physics courses. We used the generating functionals, the saddle point approximation, and the rest is just take the derivatives of the expressions we already obtained, solve for one in terms of the other one, and eventually x0, by the way, will turn out to be e to the power minus beta. If you define x0 to be e to the power minus beta, and I will just turn out to be e to the power minus beta ei, which was the result we had already obtained. So, which is kind of, well, once you fill in these steps, which will be the proof that in the thermodynamic limit for large systems, the most probable value or the average value, they will all be the same thing. There won't be any difference between them. So you can work with one or the other one, whichever one you find easier to deal with. Any last questions? Next week, we will start doing some explicit applications of what we had already learned to some physical systems. And we will also look at negative temperatures. Negative absolute temperature. They exist. We even create them experimentally.
Smaller than absolute. Smaller than 0.
Well, I rather prefer the expression larger than infinite Kelvin. They are hotter than positive temperatures.
No, I don't really.
Hmm?
No, I really don't understand.
Okay, good. So now you have motivation to come to next week's lecture.
Is there a rule for the heat?
Hmm?
Is there a rule for the temperature? At some point.
Kind of. Yeah, in a sense, yes. Yeah, we will discuss next week. So see you next week then.